What if Earth isn't just lucky to host life, but miraculously unique? We're talking about a cosmic lottery where our planet won against truly impossible odds. Every wobble, every breath, every degree of tilt makes us the only known oasis in a vast, empty universe, suggesting life might be far rarer than we imagine. Our investigation begins on the grandest scale. Our address in the Milky Way galaxy. We see galaxies as serene, beautiful swirls of light. But, in reality, they are violent, chaotic places. And just like real estate, for life, it's all about location, location, location. Every galaxy has its own habitable zone, a narrow, life-friendly ring. If you get too close to the galactic center, you're in a maelstrom of lethal radiation. Star density is immense, which means a terrifyingly high rate of supernova, exploding stars that sterilize their cosmic neighborhoods with gamma-ray bursts. The supermassive black hole at the core, Sagittarius A, is a high-energy engine spewing radiation that would shred the DNA of any budding life form. Our solar system is safely parked about 27,000 light-years away, far from the chaos. But you can't be too far out, either. Head for the galactic rim, and you hit a different but equally fatal problem: poverty. The outer regions are metal poor. In astronomy, metals are any elements heavier than hydrogen and helium. These are the building blocks of rocky planets and life itself. Carbon, oxygen, iron, silicon. They're forged in the hearts of massive stars and scattered by the very supernova that make the core so dangerous. In the sparse outer rim, there simply isn't enough raw material to build a planet like Earth. So we're in a narrow, life-sustaining ring. This fact alone dramatically shrinks the pool of candidates. But even inside this safe zone, there's another layer of suspicion. Our solar system is on a very peculiar orbit. We move in a nearly circular path at a speed that almost perfectly matches the rotation of the galaxy's spiral arms. Why does that matter? The spiral arms are stellar nurseries, packed with intense star formation, and you guessed it, more supernova. If our orbit were more elliptical, or at a different speed, we'd regularly plow through these cosmic shooting galleries. Each pass would risk a nearby supernova, an event that could trigger a mass extinction or even boil our oceans dry. Instead, we're in a state of co-rotation, surfing the galactic wave, staying in the quiet space between the dangerous spiral arms for huge stretches of time. This orbital resonance is not a given, it's a specific and likely rare dynamic. So before we even look at our star or our planet, our simple galactic address has already filtered out a massive number of contenders. We're not just in the right city, we're in the perfect, quiet, well-provisioned suburb. Now for our star, the Sun. We've always assumed it's completely unremarkable. But the most common type of star in the galaxy isn't our G-type sun. By a huge margin, it's the Red Dwarf, or M Dwarf. Around 75% of all stars in the Milky Way are red dwarfs. This creates a stunning paradox. If life were common, the overwhelming statistical probability is that we should be orbiting a red dwarf. The vast majority of intelligent observers in the cosmos should look up to see a dim red sun. But we don't. So why aren't we orbiting a red dwarf? The answer seems to be that red dwarfs are fundamentally hostile to life. On the surface, they look promising. They live for trillions of years, offering a huge, stable runway for evolution to take off. But that promise hides a deadly reality. First, because red dwarfs are dim, their habitable zone is huddled incredibly close. A planet in that zone would almost certainly be tidally locked, with one side in perpetual scorching daylight and the other in an endless frozen night. A sliver of twilight in between might be livable, but it would be a world of planet-scouring winds as the atmosphere tried to balance the extreme temperatures. Second, and far more damning, is their violent temper. Young red dwarfs are flare stars. They erupt with unpredictable high-energy flares, far more powerful than anything our sun produces. Even an ancient, quiet red dwarf, like Barnard's star, was found to be in a state of high flare activity for about 25% of the time it was observed. For a planet huddled close, these flares would be catastrophic, stripping away its atmosphere and sterilizing its surface. Finally, there's the pre-main sequence problem. Before a red dwarf settles down, it spends up to 1 billion years in a hot, bright youth. Any planet that will eventually be in the habitable zone gets cooked during this phase. It's doomed to become a sterile, Venus-like hothouse before it ever has a chance. Our Sun, a G-type star, is a paragon of stability. Its habitable zone is far enough out to prevent tidal locking. Its flare activity is mild. It provides a stable, consistent energy output that has allowed life to thrive for billions of years. It's a gentle, nurturing star, and it's a minority. Just by being born around a star like ours, we've already beaten odds that eliminate 3/4 of all star systems in the galaxy. So, we've got the right address and the right kind of star. But the architecture of our solar system, the arrangement of its other planets, is another critical filter that our system seems to pass in a way that's proving to be exceptionally rare. As we've discovered thousands of exoplanetary systems, a common pattern has emerged that looks nothing like ours. Many systems feature super-Earths orbiting incredibly close to their stars. Our solar system is different. We have no super-Earths. Our inner system has 4 small rocky worlds, while the gas giants are way out past the asteroid belt. This specific layout is profoundly important, and we likely have Jupiter to thank for it. Jupiter acts as our solar system's gravitational bouncer. In the early days, Jupiter's immense gravity is thought to have swept through the inner regions, disrupting the formation of larger planets and clearing out the neighborhood. This allowed a small, rocky planet like Earth to form and maintain a stable, nearly circular orbit. Without Jupiter, Earth might never have formed at all. For a long time, Jupiter was also seen as a cosmic vacuum cleaner, shielding us from comets and asteroids. However, this is a point of scientific debate. Some recent models suggest that while it deflects some objects, it might actually redirect others towards us. Its net effect is complex and uncertain. But what's clear is that Jupiter's presence fundamentally sculpted our solar system's uncommon architecture. The clockwork stability of our solar system is another anomaly. Our planets move in remarkably stable, nearly circular orbits. Many exoplanet systems we've found are chaotic, with planets on eccentric, crisscrossing paths. Our calm, predictable system allows for a stable climate over geological time, another prerequisite for the long, slow process of evolution. It's one more piece of the puzzle that had to be just right. Zooming in, we find perhaps the most striking feature of our world, our moon. For a rocky planet, it's freakishly large. Mercury and Venus have no moons. Mars has 2 tiny captured asteroids. Our moon is over 1/4 the diameter of Earth, essentially a sister planet. And without it, we simply wouldn't be here. The leading theory is the giant impact hypothesis. Around 4.5 billion years ago, a Mars-sized protoplanet we call Theia slammed into the proto-Earth. The collision was cataclysmic, vaporizing the impactor and a huge chunk of Earth's mantle, spewing a massive ring of debris into orbit. Astonishingly, some recent high-resolution simulations suggest that from this debris, our moon may have coalesced not over millennia, but in a shockingly short time, perhaps only a matter of hours or days. This violent birth had profound life-giving consequences. First, stability. Every planet's axis wobbles. Without a large moon as a gravitational anchor, that wobble can be chaotic. Mars's axial tilt is thought to have swung wildly, leading to catastrophic climate instability. Our giant moon acts as a gyroscope, keeping Earth's axial tilt in a narrow, stable range. This stability is the very reason we have predictable seasons. It keeps our climate from descending into chaos. But Theia's impact did more than just give us a stabilizer. It may have been a delivery service for the ingredients of life. The early Earth may have been a dry, barren world. The impact likely delivered a huge portion of Earth's water and carbon, seeding our planet with the raw materials for biology. The impact also supercharged Earth's rotation, initially giving us a day that was only about 5 hours long. Over billions of years, the moon's gravity has acted as a brake, slowing our rotation to the familiar 24 hours and creating powerful ocean tides. These tides created vast tidal pools, dynamic chemical laboratories that may have been the perfect place for concentrating organic molecules and sparking the first self-replicating life. The rhythm of the tides, driven by our anomalous moon, might be the very rhythm to which life itself first learned to dance. Even with all external factors aligned, a planet can still fail. To stay habitable for billions of years, it needs a living geology. On Earth, that's plate tectonics. Our crust is broken into massive plates that slowly drift and grind against each other. This process, which seems destructive, is actually Earth's global thermostat, and it may be one of our planet's rarest features. It works through the carbonate-silicate cycle. CO2 in the atmosphere dissolves in rainwater, erodes rocks, and gets washed into the oceans, where it's eventually locked into seabeds. Plate tectonics then drags this carbon back into the mantle, where it's eventually released by volcanoes. This cycle acts as a planetary thermostat. If Earth gets too hot, weathering pulls more CO2 out of the air, cooling it down. If it gets too cold, volcanoes continue to pump CO2 in, warming it up. Without plate tectonics, Earth would have likely become a frozen snowball or a boiling cauldron like Venus. This leads to the final, most profound filter: life itself. The standard view is that life arises on planets that are already habitable, but a more radical idea, the Gaian Bottleneck, flips that script. It suggests that habitability isn't a precondition for life, but a consequence of it. According to this hypothesis, life might emerge frequently on young, wet, rocky worlds. But the default fate for most of that life is quick extinction. To survive, life must not just exist, it must seize control. It must evolve fast enough to create feedback loops that regulate the planetary environment. Most life, on most planets, fails this test. The planet either overheats or freezes, and the brief flicker of life is snuffed out. Earth is where life didn't just survive, it won. Early microbes fundamentally re-engineered our planet, creating the very atmosphere that complex life depends on. In this view, life isn't a passenger, it's the pilot. And most pilots crash their planets before they even learn to fly. Each of these filters, galactic location, star type, system architecture, a large moon, plate tectonics, a Gaian regulatory system, is a hurdle of staggering improbability. When you start to multiply these low probabilities, the number of potential Earths plummets. One 2024 study posted to the ArcSiv preprint server attempted to quantify this. Researchers ran a comprehensive multivariate analysis on 517 confirmed exoplanets, evaluating them against 8 key parameters for habitability. The result was stunning. Of the 517 planets, only 3, including Earth, met all the criteria. That's just 0.6%. The same analysis found that a staggering 75% of planets fell into a category they called good star, poor planet, orbiting a stable, sun-like star, but unsuitable themselves. Now, this is just one model with a limited dataset and specific criteria. This 0.6% figure isn't the final answer, but it is a chilling, quantitative echo of the silence from the stars. It suggests Earth-like planets are profound statistical outliers. This entire line of reasoning is known as the rare Earth hypothesis, and it has powerful critics. First, there's the argument from sheer scale. The universe is so vast that even 1 in a trillion chances can become new certainties. With 400 billion stars in our galaxy, a 1 in a billion chance still leaves 400 potential Earths. Second, there is the charge of carbon chauvinism. The rare Earth hypothesis is built on the assumption that life must be like us. Critics argue this is a failure of imagination. We are simply listing the conditions that led to our existence and declaring them the only conditions. Could life not exist in methane lakes or be based on silicon? We only have one data point, Earth, and it's scientifically perilous to draw universal conclusions from a sample size of 1. Third, many of the rare factors are being challenged. Is a large moon really necessary? Is plate tectonics truly rare? Is Jupiter a protector? One by one, the pillars of the rare Earth case are being questioned, as they should be. This debate gets to the very heart of what it means to be human. It's a case that involves astronomy, geology, biology, and philosophy. And it's an investigation we want to continue with you. What do you think? Are we a beautiful, terrifying anomaly? Or is it just a matter of time before we find our galactic neighbors? Let us know your thoughts in the comments. These discussions are how we, together, explore the biggest questions there are. And if you're fascinated by these cosmic mysteries, consider subscribing. We dig into these profound questions every week. And by joining our community, you help support content that explores the cutting edge of science and the deepest parts of the human experience. So, where does this investigation leave us? Standing on a pale blue dot, looking out into the silent darkness. On one hand, the comforting idea that we're average, backed by the mind-boggling scale of the cosmos. On the other, the rare Earth hypothesis, a sobering and evidence-based case file of all the cosmic flukes that had to align perfectly just for us to be here. The final answer isn't in yet. We may be on the cusp of finding it, as the James Webb Space Telescope begins to analyze the atmospheres of distant worlds. But for now, the evidence is leaning toward a conclusion that is both humbling and empowering. The story of our planet is not a common tale told 1 billion times over. It's the story of a cosmic tightrope walk. It's the story of surviving the galactic shooting gallery, of being born to a gentle star, of having a giant bouncer shape our solar system, of being gifted a freakishly large moon in a cataclysm, and of life itself grabbing the controls of a planet and refusing to let go. If we are as rare as the evidence suggests, if we are a 0.6% anomaly, a winning ticket in a cosmic lottery of impossible odds, then it changes everything. It means the silence from the stars isn't a mystery. It's the natural state of things. It means this world, this thin shell of life on a fragile rock, might be the only outpost of consciousness in our entire galaxy. And that raises the final question. Does being a statistical impossibility make us feel small and alone? Or does it make our existence the most precious event in the history of the universe? It suggests that the light of consciousness that has ignited here is a treasure beyond measure, a single precious flame in the vast, empty dark. And it bestows upon us, the improbable survivors, a sacred and terrifying responsibility. To protect it, to cherish it, and to ensure that this beautiful, impossible anomaly does not, through our own folly, become just another part of the great cosmic silence.